pleasure to be invited here to share with you some of our work on Dye-Sensitized. And I'm going to specifically concentrate on photophysical and electrochemical impedance spectroscopy. Next, please. Our last speaker did mention we have 3 generations of solar cell. The first generation started in 1950 with the application in aerospace, and then in the middle 50, as compound solar cell was thin type has been developed. And you take a look at those first 2 generations, the efficiency is quite high. They are all in double digit for single cell. And even for the module, most of the cells are in double digit efficiency. Now, when we start to talk about the 3rd generations, which started middle 70, for Dye-Sensitized, for example, even today, we are still talking about 11.18%. And for the organic solar cell, we're talking about 6 to 7%, rather low. With this audience, I probably don't have to mention why we are going backward to a very low efficiency. The momentum of the motivation to do this kind of solar cell is simply for the reason of economic reason. Here you need to have a high energy consume instrumentation for the process to make this type of thin film. But here simply you can make the cell can be made in ambient environment. Again, this is the working principle of Dye-Sensitized. There's some undesirable reactions which also occur in addition to the desirable electrochemical reactions. For example, when you shine the light from left-hand side, you actually generate you excited the dye, and then the dye injects electron, and the electron has to go through the thin film of titanium dioxide and transport out of the system. However, the electron in the conduction band can be captured by the oxidized dye, S+, and go back to the ground level. And also, the electron in the conduction band can be captured by triiodine here, and also here at the photoanode, which is consume your electron here, so that your electron output will be decreased. So this will decrease your short circuit current, this process and this process. And the other 4 processes are the process that you want. Now, as our last speaker also mentioned, that there's advantage to make this kind of solar cell because of it is a semi-transparent solar cell, and it is the only type of solar cell that has this kind of property, so that it can be integrated into the existing building, the so-called BIPV. However, there's a big disadvantage so far in terms of reliability, long-term stability due to the leakage of electrolyte, and also again the efficiency is still single digit, even double digit efficiency has been reported. Now this is a way, a very systematic way you can find in the existing literature to make a titanium dioxide, anodized titanium oxide film. The pretty standard method is to make a precursor first and you autoclave at a certain temperature. And this temperature is very critical because later you will find the morphology and surface area, etc. depend on your autoclaving temperature. And you add some polymer to the precursor before you heat it up to a certain temperature. Now, the draw of this polymer is to suspend those colloidal, and so that you can later burn those polymer and create micropolar structure or mesopolar structure. And this step is also very critical in order to get enough surface area with right pore size. You need to heat up to 450 degrees C to 500 degrees C, especially at a certain rate. If the rate is too high, you will destroy the nanostructure. And if it's too low, it will take too long to get the right structure. So the temperature rising step is also a key to this process. And sometimes the thin film has to be coated several times in order to get enough thickness. For example, with a traditional N3 or N719 commercial dye, you need about 15 to 20 micrometer to get enough efficiency. So in other words, if you have 5 or 6 micrometer per coating, you need to have 3 times in order to get right or enough amount of dye absorbed on or inside the pore. This is about the size of the nanoparticle of titanium dioxide, which is around 20 nanometer, which is also about the cross-sectional or effective cross-sectional area of commercial N3 dye. Now, I'm going to also talk about the organic dye, which is made by my co-worker at the Academia Sinica in Taiwan. Remember, this is a familiar functional group that Professor Kim talked about, and this will give us a very good donor-acceptor structure so that we can get a high efficiency solar cell. Now, the efficiency achieved by this organic dye is about 90% of ruthenium-based commercial dye, which I'm going to talk about in a minute. This is the sandwich structure. There's no need to mention too much, except in order to make a good, long-lasting device, you need to have not only a sealant or spacer, but you need a good sealant for air, for oxygen, and water. So in order to make this device a success, last long enough, you need to have not only an initial measurement, but have a good sealant. Experimental condition is pretty much the same as that we found in literature, except here we try to use different dye, and counter-electrode is platinum, which was spotted on FTO glass. Now the dye I'm going to talk about is two kinds. One is ruthenium-based commercial dye, and the dye called CYC-B1 dye, which was synthesized by my co-worker, and organic dye, the one that I mentioned, was synthesized by Professor Lee at Academic Sinica. This is the organic dye, and this is the inorganic ruthenium-based dye. Actually, people did some theoretical modeling regarding how to maximize the photocurrent out of this system. And many reactions occur inside the dye-sensitized solar cell has been modeled. For example, this is the injections of dye of electron to the titanium dioxide, and here you will generate the consumption of the combinations of electron. So plus, the 2 plus and 2 minus, and this is so-called electron population balance. So actually you want to maximize this photocurrent, and this photocurrent has to do with the thickness of the titanium dioxide, and also has to do with the amount of dye absorbed on this titanium dioxide thin film. Now, just give you one example how important it is to have a right cation. In dye-sensitized solar cell, we talk about iodine instead of lithium perchloride, which was used in lithium-ion battery. Now, everything remains the same. The platinum counter-electrode, titanium photoanode, and N3 dye. The only difference is this cation. And the cation, and you look at the so-called photovoltaic transients. You shine the light to the cell, and immediately you will find a photovoltaic decay. And from this decay, it is well known that this relaxation will give you a time constant. Exponential decay give you a time constant. And this time constant is 6.6 milliseconds, and this time constant is 18 milliseconds. Apparently, iodines give you a longer electron lifetime. The way you define the electron lifetime is from this time constant. And everything looks very similar, the trend looks similar. However, this is the normalized photovoltaic. So that time we're talking about with this iodine is much longer than the system with lithium perchloride. So that tells us with iodine, the electron within the transport across this titanium dioxide side takes longer, and it should have better performance in terms of short circuit current. So that's why iodine is needed in this system rather than perchloride ion. Now, with this system, you can also estimate the thickness of that titanium dioxide you need to get the maximum current out of the system. Here, you already know the thickness of the film, and from that kind of electron, you can calculate the diffusivity of electron inside the titanium dioxide film. And this is was made by random motion. Remember, you don't have long aspect ratio of titanium dioxide film. You have a very polar structure, and electron will always go through the smallest resistance. So the motions of electrons not go in a straight way, but in a curve and a random way. So this will approximate the diffusivity of electron within the same film. And for 20 nanometer titanium dioxide, you can calculate the diffusivity around this order of magnitude. Now, once you know the diffusivity, you know the lifetime of electron inside the film, you can calculate the theoretical maximum length you need for titanium dioxide, which is about 18 micrometer, and that satisfies ourselves that we only need about 3 coatings for titanium dioxide. Now I will get into one of our earliest organic dye system, which is carbazole, and I'll get into another senior fluoro dye system, and then I get into the leucinium dye. And those two dyes are cooperated with coworker. Now let's give you a quick review of some organic dye made by Arakawa. The efficiency we're talking about is around 6% or so. And here you have 7, but on the other hand, some of the coworkers come up with the very low efficiency dye. And for example, with the underlying series, you can sometimes get to exceed 8%. And as you also know, professor at the Korea University also achieved more than 80% with organic dye. So this is a well-known literature. I don't have to get into too much. But for the leucinium-based dye, usually the number is higher or bigger. For example, N719, this can achieve 11.18. But not all of them can reach double digit. For example, some of them only get 6 or 7 or 9%. And Agitas group also pioneering some of this leucinium dye. Now, the carbazole dye I'm going to talk about. I'm going to focus on its photophysical property, namely its electron lifetime. Now, you look at the carbazole's 3 chemicals we synthesize. Every chemical has this group, but the chemical structure is different. Now, we want to ask ourselves, theoretically, which chemical or which dye will perform best in terms of efficiency. So naturally, what you do is to perform homolumo experiment, and you get something like this, and transport into this diagram, you will look something like this, and you will say to yourself, because number 6, carbazole dye, behaves so different, and with the right homolumo level, this should perform best. So you take a look at the final performance compared to the N3 dye, which we achieve around 6.95%. The number 6 actually did not perform the best. The best comes with number 4. Number 4 here. So you cannot simply tell by homolumo pair. So something else has to be important. So we go back to our very basic measurement, that is IPCE. It also tells us the number 4, CV number 4, perform the best in terms of high IPCE. But when we do the photophysical measurement, we can find that this electron lifetime actually was the highest among all 6. So, but the electron diffusivity did not vary much. But this electron lifetime from number 4 actually this gives the highest efficiency. So this, from this regard, it is consistent to have a very high performance for number 4. Now, with the senior dye, we have 4 dye which we synthesize all with the same ending group. But here you have silophane, here you have benzene, and here the difference is cesium, but this is sulfur. So again, we try to find the homolumo and decided that maybe dye number 4, S4, will give you the best performance in terms of homolumo band gap. However, if you look at the cell performance, actually S4 did not perform the best, but S1 here and here are consistent. Always S1 give the best performance. So we need to think about the electron lifetime. When you measure the electron lifetime, it tells you that the S1 actually give the highest electron lifetime, 6.5 milliseconds compared to 17 or so for N3. That explains why S1 is still, the efficiency achieved is still lower because compared to N3 dye. But for S3 and S4, they are in the same category. And S1 and S2 are in the same category. So that also explains this S1 and S2 in the same group, and S3 and S4. But if you have this perchloride electrolyte, now the electron lifetime doesn't tell you the story, but only lithium iodide. Now move to another dye, FL dye. If the chain length is very short, n equal to 1, we have achieved efficiency of 5.23 as compared to N3 of 5.25. Remember when we published this work, this was in 205, we only used about 2 layers of titanium dioxide, which is around 12 micrometer. And efficiency achieved with this dye, FL dye, is about 90% of N3, 5.23 compared to 5.5, which is around 90%. Now, if we make it thicker, it will help. And the efficiency achieved by this dye is about 7.19, and N3 is 7.87, the same dye. And again, 90% of efficiency is preserved compared to N3. Now, later on, we made different dye, and all we did the similar approach. Measure the absorption coefficient and try to correlate this with performance. Now, if you think if the dye 5 and 6 will perform best, it can be very wrong. Actually, the dye 1, FE dye 1 performed the best, not 5 and 6. So the molar absorption coefficient does not tell you a whole story. Again, for different dye, if you think this number 2 will give the best performance, according to this, that's probably wrong, because this give you highest. So we have to try to correlate the performance not only with the absorption coefficients, but with the electron lifetime. I'm not going to show you too many dye we synthesized, but try to get to one of the ruthenium dye system. This is a dye system obtained from Professor Wu and his group. Again, this is ruthenium, and the difference is here. Now, this dye is so different. CYCB1 is so different compared to all the other. So we think this should give you the best performance as far as the metal to ligand charge transfer is concerned. Again, we did some HOMO and LUMO. There's not much difference between this and this. But if you look at the performance, we get around 9% for CYCB1 as compared to N3 of 8.57%. Although the other dye are not perform as well as CYCB1, This is our first evidence that our dye can exceed the existing commercial dye of about 10% in terms of efficiency. In terms of electrochemical measurement, it is the second resistance, which is charge transfer resistance between electrolyte and titanium dioxide that will determine the cell performance. So the cell performance of M3 is determined by this charge transfer. So CYCB1 performs the best, which should give you the lowest charge transfer resistance. Here, the resistance lowest. Now, in terms of thickness effect, it does play an important role. For the M3 dye, you need to have a 3 or 4 coating to get enough cell efficiency. But for our homemade dye, you only need 2 coating to reach the saturation of performance. This is just another version of efficiency in terms of current and open circuit voltage. Now, again, if you look at this AC impedance, you can easily find you need to have a 4 coating, 1, 2, 3, 4, to stabilize the efficiency, but the resistance. But you need only 2 coating to get charge transfer resistance stabilized. So in terms of charge transfer resistance, our dye has some advantage over N3, which shows lower resistance. Again, with photophysical measurement, our dye also have a longer lifetime. Another dye, which is SA1s, we synthesize, also have advantage of competing with N3. Go here, N3 is around 8.42 and SA1 get 9% or so. Again, our dye have a longer efficiency in terms of electron lifetime. Now, here you have bipyridine, silicon, and carbidol system. And here you have a short chain. Here you have a longer alkyl group, long chain. And we want to compare this. And you can see, compared to N3, both, whether it's long or short, also get a higher absorption coefficients. And there's not much difference in terms of band gap, homo-lumo, but the cell performance improved with a very short chain. And here is N3. So my conclusion is that the transient photovoltaic technique can be a very important tool to judge the performance of DSSC before making a real cell. And also organic dyes such as the S1, S2 have a very high efficiency, but the efficiency is not high enough to compete with the existing dye. However, the dyes such as Dye-1 we synthesize get 90% of efficiency as compared to N3, and which tell us that there's still a lot of room for improvement because organic dye advantage of making it cheap. And CYC system, whether it's CYCB1 or CYCB6, all have exceed the efficiency achieved by commercial dye. So in conclusion, I would like to acknowledge my co-worker, Professor Lee at Academic Sinica, Professor Wu at the National Central University, and my previous postdoc and graduate student. I'd like also to acknowledge Professor Lee at the Chemistry Department of National Taiwan University for his offer to my lab and our founding agents. And I thanks my students for their hard work. Thank you for your attention.